Example 2, we're looking for electric field strength at a point in space where the alpha particle experiences an acceleration of 3.60 times 10 to the 9 meters per second squared. So what they're giving you in this case, we want to know the electric field strength again. That's what we're being asked. We know we have an alpha particle. So when you look on your data sheet, you've got the charge of an alpha particle. The mass of the alpha particle, if you want to get this off your data sheet, 6.65 times 10 to the negative 27 kilograms. The charge on the alpha particle is 2 times the elementary charge, which means it's 2 times 1.60 times 10 to the negative 19 coulombs. This is all off your data sheet. As soon as they refer to alpha, electrons, protons, and neutrons, you have their charges and you have their masses on a table. We also know this thing experiences an acceleration of 3.60 times 10 to the 9 meters per second squared. So this is the electric field resulting from an object inside. This is the one experiencing. So the alpha particle is the test case. In this case, it's electric field equal to electric force over charge. Now the trick in this question is if it experiences an acceleration, that electric force, in this case, can be written as ma. Newton's second law tells us that all forces, net forces, cause an acceleration. So the electric force in this case can be written as ma. If I put these two formulas together, my electric field can be written as mass times acceleration of the alpha particle divided by charge. I have all those numbers, so the electric field can be equal to 6.65 times 10 to the negative 27 kilograms times the acceleration, 3.60 times 10 to the 9 meters per second squared, divided by the charge, 2 times 1.60 times 10 to the negative 19 coulombs. So the electric field, when you punch all this in, 6.65 to the exponent negative 27 times 3.6 exponent 9 divide by the charge, you should get 74.8 to 3 sig digs newtons per coulomb as the electric field in this case. Remember two things in this question. One is the alpha particle was the test object in here. This is the one that the force was being acted on. So this was the object inside the field. And because it doesn't talk about any kind of gravitational force acting against it, we didn't worry about it. Now, back in the notes, you might remember that there's quite a few comparisons between electric fields and gravitational fields. One quick piece of advice: if you look at the constants between electric fields and gravitational fields, that 8.99 times 10 to the 9 is a very big constant, where the gravitational constant, 6.67 times 10 to the negative 11, is a very small constant. You'll see very quickly that gravitational fields and gravitational forces are incredibly small compared to electric fields and electric forces. You don't need a very big mass to get a really strong electric field strength. But to get a really strong gravitational field, you need a huge mass, like size of the Earth type masses, to get very strong fields. So when you do comparisons of these very tiny objects like alpha particles, electrons, protons, their masses are so small that the gravitational forces and the gravitational fields wouldn't carry to the number of signigs, wouldn't change your number. They're just too small to be used in a comparison. And it's because of those constants in those formulas.